Hi, this is my talk about Blavan, the R package for Bayesian structural equation modeling. I'll say a little bit about the history of the package as well as some of its functionality. Um, so, what is Blavan? Well, we have Bayesian structural equation models. Um, Structural equation models generally come from the field of psychometrics. There's traditional applications involving measuring unobservable traits, say things related to aptitude or ability. Um, this family of models is interesting to me, especially because it's related to lots of other types of models. It's related to directed acyclic graphs and causality research. It's related to mixed models, time series models, others, and it's a large family. So if you can find good estimation methods for this family, you potentially have good estimation methods for lots of other models that you might be interested in. Blavan is related to an older R package, Lavan, which does structural equation models in a non-Bayesian way, typically maximum likelihood and some least squares methods. Um, Lavan is very popular. Eve, the developer of Lavan, had a keynote talk at this conference in 2017 that has a user-friendly way for specifying these big structural equation models, lots of different estimation methods and summary methods. But for my purposes, I'm especially interested in this functionality for converting model specifications to model matrices. I use a lot of that in Blavan, so in many ways, Blavan is just some building blocks on top of Lavan and some bridges with other packages. So Lavan is a big piece. Also, we have the Bayesian functionality. So Blavan is calling Stan or JAGS to actually do the model estimation. Um, of course, software like Stan or JAGS is very, very flexible. For applied users, coding up models can be tricky or difficult sometimes. Going along with that, there's lots of ways to code the same model. And some ways are very, very slow and inefficient, others are faster and more efficient. And so in Blavan, users can use the model specification from Lavan, and then that's converted automatically to code for Stan or for JAGS. And that helps people get to these Bayesian versions of the models in a relatively fast and easy manner. So here's the steps similar to BRMS that I've kind of outlined already. The user specifies a model first using the Lavan model specification syntax. This specification is then converted to a model, matrices and parameters and so on. And so I'm using Lavan's functionality to do that conversion. Now that conversion is further converted into Stan or JAG syntax. So a big part of Lavan is just doing that translation from Lavan to Stan or JAGs. After that, the model is estimated via MCMC and Stan or JAGs. And then finally, we get the results back, and Blavan can summarize the model in various ways and provide different types of diagnostics. So that's a little overview of how it works, a little history of the package. Well, this is started around 2015. And initially, we were just myself and Eve, the Lavan developer. We tried to convert some Lavan models to JAGs at that time. and we had to develop some tricks to get those models to work all the time. There's a JSS paper about that. After that, we moved to Stan and tried to take a similar approach to what we did for JAGS and Stan, and that worked. It wasn't always totally efficient. I think our approach just wasn't right initially. But since then, we've taken a new approach in Stan with the help of Ben Goodrich and some others, where we have one pre-compiled model that will fit any structural equation model that the user requests. And that's really helped our speed and efficiency, and it's helped make the package usable, I think. Alright, so that's a little bit of history, and now we'll just run through some functionality with a running example. So for our example, we'll just use a fairly simple factor analysis model. If you know this Holzinger-Schweinfurt data set that's included with lavaan, this example will probably be familiar to you. Basically, we have 301 students, test scores. Every student has 6 test scores. 3 of them are about visual perception, 3 of them are about verbal comprehension. And so we have this factor analysis model where there's a visual factor that is underlying these 3 tests of visual perception. Then there's another factor underlying these tests of verbal comprehension. If you do path diagrams, this is what our model looks like. Our Y1 to Y6 are the, for one student, the 6 test scores. And then we have our first factor, this eta1, that's associated with the first 3 variables. And then our second factor, eta2, that's associated with the second 3 variables. And those 2 factors can be correlated. That's our double-headed arrow here. Well, that's the path diagram version of the model. If we think about the lavaan syntax for the model, we end up with this. This slide just shows how we could specify this model and estimate it in lavaan. We have our syntax here about our first visual factor that's associated with the first 3 observed variables, and then the second factor is associated with the second 3 observed variables. And then our command to fit this model is just CFA in lavaan. So then we can move to Blavaan. Well, everything looks almost the same here. We load the Blavaan package now. Our model specification is exactly the same if we're happy with the default everything. And then our model estimation command, now we have BCFA instead of just CFA. So that's generally the case. Lots of the Blavaan commands just have a B in front of the lavaan command that does a similar thing. So this just shows that Blavaan commands and syntax is basically the same as lavaan. But there's lots of things, if you don't want to rely on defaults, or you shouldn't rely on the defaults, well, there's lots of other things we can do. We could choose how many warm-up or sampling iterations we want to run our MCMC for. We might want to choose our own prior distributions. We might want to get factor scores, or in other words, sample the factors in our model along with other parameters. Or finally, assess whether or not our MCMC chains have converged. So I'll give a quick overview of how you could do each of these. The first burn-in or warm-up and sampling iterations, well, we just have an argument burn-in and an argument sample that we could set to any numbers, whatever is desired for a particular model. I would say if we're running the models in Stan, typically these don't have to be as large as some of the older software like WinBugs or even JAGS sometimes. If we're not happy with our priors, well, we can specify our own prior distributions in various ways. Here's an example where we just take our model specification syntax from before. We had like our x1 plus x2 plus x3 before, and we can put this prior modifier out in front of one of our variables, and that's going to give a particular model parameter a specific prior. So like here we have a normal mean of 1 standard deviation of 10 prior for the loading from our visual factor to our second observed variable. We have something similar for x6 down here. So that's a way to specify a prior distribution for a specific parameter in our model. But we could also say, well, I want to set a prior for all parameters of a certain type in my model. That's what leads to this dpriors command. So you say, what are the default prior distributions that would be used if I didn't specify a prior distribution? This command dprior shows it to you here. We have all these different types of parameters in the model, like new is observed variable intercepts, alpha latent variable intercepts, lambda are factor loadings, and so on. And we have a distribution underneath each of those. So this shows you what the defaults are, but this is also the way you can modify them if you want. And I would say in many cases it's desirable to modify these. These are not going to be your best bet for every situation. So to modify them, well, we can just pass in the name of the parameter type that we want. So like in this command down here, we have lambda for factor loadings, and then we're passing that as an argument dp to our model estimation command. So in the end, we use this dp argument to change the priors for different sets of parameters. And here we use our command here is setting the loadings, those are the lambdas, to normals with mean of 1, standard deviation of 5, whereas all the other types of parameters just get the defaults that we saw in the last slide. We might be interested in sampling the factors along with other parameters, but it's very memory intensive. So for example, in our model here, there were 301 people and there were 2 factors, and every person has their own factor scores. So we end up having to sample like 602 extra parameters if we want to save the factor scores. So we don't do that by default, but there's this argument save.lv is equals true that we could include in that bcfa command, and then we'd sample all of those factor scores, or you might call them latent variables. And down here at the bottom, I have 2 examples of how we could extract information about those factor scores after we sample them. We can just get the posterior means of all of those, or this LVs one is just getting lists of all of the posterior draws for those factors. Of course, convergence is another big issue with Bayesian models, and so this is one of the nice things about R. We can rely on other packages to compute some convergence diagnostics, and then Blavon has convenience functions for extracting these. You can access a lot of these from this blav inspect command, where we ask for like the R hat diagnostics in this first command, effective sample sizes in the second command, and then the next slides will show some graphs that are coming from Bayesplot, the Bayesplot package. We have a plot command, or a plot method for the Blavon objects, and we can say which of the free parameters do we want to know about. So like in our command up here, we're looking at the first 4 parameters, and we ask for trace plots, and that's what we see down here. We get our trace plots that look pretty good. They imply the model's converged. We can ask for other types of plots, so we say plot type equals intervals. These are all different types of plots that are in the Bayes plot package, and so we're just calling those in the Blavon plot method. And so this shows us posterior intervals for 4 variance parameters here. Alright, so that's a very brief overview, but of course this is only the basics. There's lots more to do. I could say more about model comparison or fit. Multiple groups and measurement invariance, that often comes up in a structural equation modeling context. Approximate equality constraints, those are pretty new. Those will be coming out soon. Another one that I haven't mentioned is exporting the Stan model or the JAGS model so that advanced users could modify that themselves and run it. That's another possibility that you can check out the papers for some more details about that. And then finally in the future, well, I want to continue to work to improve the speed and efficiency of the methods, the estimation methods in Blavon. Also increase the functionality of Blavon, especially for handling ordinal variables and multi-level data. So that's my overview of the package. Thanks for your time. Feel free to contact me with problems or bugs, and I'll show a couple extra slides that has some further reading and further things to do. But thanks for your time.